This lesson is on the second derivative. The second derivative is the derivative of the derivative, and the notation is f double prime. And the second derivative gives us acceleration or deceleration, which is the rate of change of the rate of change. It tells us how fast the derivative is changing. And so when you think about movement, distance, if we let s of t be the position of a car, where t is hours and s is miles, then if you take the derivative of that function, then you get miles per hour, because the units on a derivative are always y units per x unit, miles per hour, and the derivative is the instantaneous rate of change. So the first derivative of a position function is miles per hour, which is velocity. Velocity is the first derivative of a position function. Well, then, if you take the derivative of velocity, the first derivative of velocity is really the second derivative of the position function. And the second derivative of a position function gives you the acceleration of the car, or the rate of change of the rate of change of the car. And the units would be this. The velocity function is miles per hour. If you take the derivative of velocity, the units would be miles per hour, or miles per hour squared. That's the unit for acceleration of something in motion, where distance is displaced. So we can have acceleration of different types of things, but it really makes the most sense when we think about position, because we get in our cars all the time and we drive a certain speed or velocity, and we accelerate and decelerate. So that's the example that you want to go back and think about when you're doing problems. Okay, so one interesting thing we can find is if you have a graph, this graph is increasing at an increasing rate, and then there's this red dot, and then it's continuing to increase, but now it's increasing at a decreasing rate. We say that this part right here is concave up, because if you took it like a wire and bent it up, it would look like this, concave up. And we say this part right here is concave down. And right here in the middle is called the point of inflection. And we know that that is the point when the function is increasing the fastest. And so if you want to know where that point is, you would take the second derivative and goal seek it to 0 to find that value. So when you're asked when is the function increasing the fastest, that is when you would take the second derivative and goal seek it to 0. So we can look at some examples now. So if we look at this first example, it says the daily oxygen consumption of a turkey embryo increases from the time the egg is laid through the time the chick hatches. In a brush turkey, the oxygen consumption can be modeled by this function here, and it's a polynomial function, and for t between 20 and 50, so we were given a domain, and we're told that c is in milliliters. Okay, where t is the time in days since the egg was laid. It typically hatches around 50 days. So t is time in days, c is milliliters, and the function is the daily oxygen consumption of a turkey. Question A says find the daily oxygen consumption 40 days after the egg was laid. Well, that's what this function here will give you. If you know the number of days, then you know the daily oxygen consumption. So A, you have to recognize, is the original function. Then B, find the rate at which the oxygen consumption is changing 40 days after the egg is laid. We're looking for a rate of change. So that would be the first derivative. And then C, find the rate at which the oxygen consumption is accelerating 40 days after the egg was laid. That's the second derivative. And then D, when is the daily oxygen consumption increasing the fastest? That is a point of inflection, and you find it by goal seeking the second derivative to 0. Okay, so when we read through the problem, we know we need the original function that relates number of days to milliliters of oxygen consumption, and then we need the first derivative. So we'll take the first derivative, and I'm not going to do any simplifying. I'm just going to write down my constant and then take the derivative of this t cubed and then write down my constant times the derivative of t squared, and then the derivative of minus 44t is minus 44, and the derivative of 95 is 0. So that's my first derivative. And then if I want to find the second derivative is the first derivative of the derivative. So I just look at this derivative and I take the derivative of it, and now I have this term, and this term has two constants now. So I'm going to bring the negative 0.028 down times the 3, because they're both constants, and then t squared's derivative is 2t. And then this term has two constants, so I'm going to bring the 2.9 down and the 2 down, and the derivative of 2t is 2, so that's it. And then the derivative of minus 44 is 0. So that's my second derivative. And so now I can evaluate both of these at 40 like we were asked. Okay, so I went and I took these three functions. I typed in my input t, c of t, c prime of t, c double prime of t, and my domain is 20 to 50, and I typed in my c of t function right here, and then my derivative I typed in negative 0.028 times 3 times t squared plus 2.9 times 2 times t minus 44. So you really don't need to do any simplifying. And then I typed in my second derivative, and I wanted to look at a graph of the original function. And I won't ever need to look at the derivative and the second derivative. Just want to look at the original function, and I can see slight concave up here, and around here it changes from concave up to concave down. And so we're going to answer all of these questions. So the first question, find the daily oxygen level consumption 40 days after the egg was laid. And so that's 40 and the original function, and that's 1,183 milliliters right here. And then the second question, find the rate at which the consumption is changing 40 days after the egg is laid, and that's the first derivative, because first derivative is a rate of change. And so the way you would interpret that is at 40 days, the oxygen consumption level is, since this is positive 53, it's increasing at a rate of 53.6. The Y units are milliliters per, the X units are days, per additional day, or per day. That's the IRC. And then question C says, find the rate at which the oxygen consumption is accelerating 40 days after the egg was laid. Well, acceleration is the second derivative, and I'm going to explain in a little bit how you tell whether it's deceleration or acceleration. It says acceleration, but it may not be. And it's not just by looking at the sign of the second derivative. It's not that. What I'm just going to show you this first time is just look at the graph right here. This is where x is 40, and it's hard to see, but this is concave down right here. And concave down means that the function is showing you an increase. It's increasing, but see how it's a concave down sort of levels off kind of eventually. And so you can see that the rate is decreasing. The function is increasing, but at a decreasing rate. And so that means it's kind of like the oxygen consumption level is increasing, but it's slowing down in the way it's increasing. So this is actually deceleration. So you would say at 40 days, the oxygen consumption level is decelerating at a rate of 0.92 milliliters per day per day. And so notice that the first part is really exactly the same sounding as the IRC. And I always want you to use the word decelerating or accelerating when you're interpreting the second derivative. Some people make an argument that you don't have to, but in this class I want you to use the word accelerating or decelerating. And then you always want to have a per day, or whatever your X unit is, per minute, per item. Always have that. You could say per day squared, but usually people prefer to just say per day. All right. Okay, so the last question is, when is the daily oxygen consumption increasing the fastest? And so that's looking for this point of inflection where it changes from concave up to concave down. And the way that you find that is by goal seeking the second derivative to 0. So you find when it's changing the fastest, when it's increasing the fastest by setting goal seeking second derivative to 0. So that's what we'll do here. Okay, and so you know now that at 34.52 days, the oxygen consumption is increasing the fastest. And you could tell what is the oxygen consumption level, 880 milliliters. You could see that it's increasing at a rate of 56.12 milliliters per day, and you can check your values here and see that it is indeed the rate of change is highest right here. Okay, so let's talk a little bit about how you can use the second derivative and some of the rules. So you can use the second derivative to help determine whether you have a maximum or minimum. So if you are tired of the eyeball method, what you could do is goal seek the first derivative to 0, which is a way of finding the horizontal tangent line, but it won't tell you whether it's a max or min. But then if you take the second derivative and you see that it's negative, then you know that it's concave down. And so if your second derivative is 0, then it's concave down, and your first derivative is 0, then you know you've got a maximum. And then if your second derivative is greater than 0, then you know you have concave up. And if your first derivative is 0, you have found a minimum. So if your first derivative is, you goal seek the first derivative is 0, and then your second derivative is negative, we know it's a maximum. If you find that your second derivative is greater than 0, then you know that you have a minimum. But here is something interesting. This little series of graphs here, if you want to know whether something is accelerating or decelerating, you can also use the first and second derivative. So if your first derivative is a positive number, then you can see it's increasing. See that? It's going up. The function is going up. the rate is increasing. If your second derivative is positive, then that means it's concave up, like we just said, and so what's going on is you are accelerating. Your function is increasing at an increasing rate because it's concave up. So the function is increasing, the rate is increasing, it's concave up, accelerating. If your function, you can see the y values are getting smaller, and your first derivative is negative, you can think of that, you can draw like little tangent lines. If you draw a bunch of tangent lines, you see you have negative slope. So you're decreasing, and then your second derivative is positive. That means it's concave up, which means that you're decreasing at a decreasing rate. So when these two signs are opposite, then you know you're decelerating. So let's say you're falling, and then you start to slow your fall. You're still falling, but you're kind of slowing down. That concavity, that concave up, the second derivative tells you about the shape of the function. It's concave up. So, but if you want to memorize if these are different signs, it's deceleration. Look at the third graph. You're increasing function, and your first derivative is increasing. I have a bunch of positive tangent lines, but it's concave down because your second derivative is negative. You can see it's bent down. So what's going on is you're increasing at a decreasing rate, and so you have opposite signs again, concave down this time, and the object is decelerating. And then the last one, your function's going down. Your first derivative has negative slopes. Your second derivative is negative, it's concave down. So what's happening is you are decreasing at an increasing rate, and that's accelerating. So basically, if you want to memorize that when the signs of the first and second derivative are the same, you're accelerating, and when the signs of the first and second derivative are not the same, you are decelerating. So look at this example. Annual sales of bottled water in the U.S. in the period 93 to 2003 could be approximated by this: million gallons, where T is time in years since 1990. Were sales accelerating or decelerating in 2000, and how fast? So this is a polynomial, so I really don't recommend it, but I'm going to take the derivative right here in Excel, but really you should write it down on a piece of paper. Okay, so T is time in years since 1990, so the domain is 93 to 2003, so that'd be 3 to 13. And then the original function is 17 times t squared plus 100 times t plus 2300. And then the first derivative is the constant 17 times. The derivative of t squared is 2 times t. Derivative of 100t is 100. And that's it. And then the second derivative, alright, take a look at this. This is 17 times 2 times t. So the derivative of that would just be 17 times 2. And the derivative of 100 is 0. Alright, just doing this in the Excel just so we can get it done quickly. I'll look at a graph. Again, you always graph the original, the given function, not the derivative or second derivative. And you can see that this function is an increasing function. Okay, we want to know were sales accelerating or decelerating in 2000. So 2000 is 10 years from 1990, so this is 2000 right here. And the first derivative is positive, and the second derivative is positive, and so when the signs are the same, you're accelerating. at a rate of 34, and let's work on the units. It's million gallons, so 34 million gallons per, and the x is year, but it's acceleration year per year. And I'll add this at, or in the year 2000. So now we have everything. In the year 2000, the function is sales were, there we go. In the year 2000, sales were increasing at a rate of 34 million gallons per year. And we know it's acceleration because those signs are the same. And yeah, so if you want to memorize that, that's very helpful using that second derivative. Okay, so this example, it says if a stone is thrown up at 10 meters per second from a height of 100 meters above the surface of the moon, its height in meters after t seconds is given by this function. What is the acceleration? So that means we're going to need the second derivative. And then what is the maximum height of the stone? Well, I typed in the original function, and then I graphed it from 0 to 20. So we're starting at 100 feet, tosses, it goes up, and then comes back down around almost 20 seconds. It comes back, hits the ground. The first derivative would be, I think I put it in here better. It would be the derivative of 10t is 10, and then the derivative of negative 0.8t squared is negative 0.8 times 2 times 8. So let me adjust that. Okay, and then the second derivative is the derivative of the derivative, so it would just be negative 0.8 times 2. It would be a constant. So you can see when you drag it down, the second derivative isn't going to change. And so now, since we're looking at the graph, we can look at these derivatives here. See right here, from about 0 to 6 seconds, the first derivative is positive and the second derivative is negative. So this is deceleration, which makes sense. You throw the stone up and gravity is taking hold, and so it's increasing at a decreasing rate. That's deceleration. And then from here on, your first derivative is negative, your second derivative is negative, and that's acceleration, because at a certain point gravity really starts to take over, and this is decreasing at an increasing rate. So this tells us concavity, concave down, but remember, when the signs are the same, you have acceleration. So the acceleration, we know, is 1.6 meters per second, and that's constant. And then to find the maximum height of the stone, do you remember how to find a maximum? You find a maximum by taking the first derivative and goal seeking the first derivative to 0. And here we see that this is a minimum or maximum. The first derivative doesn't tell you which, but since you're looking at the concavity, if it's concave down, then that's a maximum. So we now know that at 6.25 seconds we have a maximum, and the maximum height of the stone is 131.25 meters. Okay, so let's go to our lab manual, page 57, and take a look. I think that's the page number. I might be looking at an old lab manual, but second derivative, number 1, the population of Americans age 55 years or older as a percentage of the total population is approximated by the function f of t equals 10.72 times parentheses 0.9t plus 10 to the 0.3, where t is time in years since 2000. We're asked to find the second derivative and then answer the question, is the population of Americans age 55 years and older as a percentage of the total population accelerating or decelerating in 2010? Justify your answer, and we'll go ahead and make a interpretation. So this is going to be a tricky derivative. We have to take the first derivative and then we have to take the derivative of the derivative. I'm going to write down what t is. T is years since 2000. And F is percentage of the total population. Okay, so the first derivative of f of t is f prime of t, and that's a constant. It's not going to be a product rule, so I'm just going to bring 10.72 down, and then when I want to take this derivative I have to use the chain rule, so this would be 0.3 times 0.9t plus 10, and then reduce that exponent by 1. 0.3 minus 1 is minus 0.7. So that chain rule is the derivative of the outside, 0.3 times this to the negative 0.7 times the derivative of the inside, which is 0.9. So that's the first derivative. So we have this times this times this times that. And I'm highlighting this because you can at this point use Excel and clean this up. What would you do though? You would multiply these constants, 10.2 times 0.3 times 0.9, and you get one number. You can put it in the front, and then you can take the second derivative of that. Well, I'm going to try to show you that you don't really have to do that. You may not like this, but I'm not going to go switching into Excel and simplify. I know this constant rule is my favorite rule, and when I take a derivative, if it's a constant being multiplied, I can just bring it down. So I'm going to bring down 10.72. I'm going to bring down 0.3. I'm going to bring down 0.9. Those are all my constants, and all I have left to do is take that derivative. So chain rule again, that's going to be negative 0.7 times 0.9t plus 10. Reduce this by 1, so that's now negative 1.7 times the derivative of the inside, which is 0.9. So that's the second derivative. And when you're typing this in, you could say that that's 0.9 squared, or you can just type in 2 0.9s. But now I'm ready to put it in Excel. Okay, so we will put in, our input is t, original function, first derivative function, second derivative function. And we know we want time since 2000. We want to find 2010. So we'll just go ahead and put 10 in. Original function 10.72 times 0.9 times t plus 10 to the 0.3. Then the first derivative, 10.72 times 0.3 times 0.9 times parentheses 0.9 times t plus 10, close parentheses, caret negative 0.7. So I went and changed the order. I typed all my constants in, and then my binomial to the negative 0.7 power. And then my second derivative, 10.72 times 0.3 times 0.9 times 0.9 times negative 0.7 times 0.9 times t plus 10 caret negative 1.7. So there's a lot of constants. I'm going to check my work because I went a little out of order, but I have them all. Okay, so now we found the second derivative is the population accelerating or decelerating in 2010. Well, remember we look at these signs, and if they're different, it's deceleration. So at or in 2010, the population of Americans aged 55 years or older is is decelerating at a rate of 0.0122, and it's a percent, so let's say it's 1.22% per year. Okay, so let's go to our lab manual, page 57, and take a look. I think that's the page number. I might be looking at an old lab manual, but second derivative, number 1, the population of Americans age 55 years or older as a percentage of the total population is approximated by the function f of t equals 10.72 times parentheses 0.9 t plus 10 to the 0.3, where t is time in years since 2000. We're asked to find the second derivative and then answer the question, is the population of Americans age 55 years and older as a percentage of the total population accelerating or decelerating in 2010? Justify your answer, and we'll go ahead and make a interpretation. So this is going to be a tricky derivative. We have to take the first derivative, and then we have to take the derivative of the derivative. I'm going to write down what t is. T is years since 2000. And f is percentage of the total population. Okay, so the first derivative of f of t is f prime of t, and that's a constant. It's not going to be a product rule, so I'm just going to bring 10.72 down, and then when I want to take this derivative I have to use the chain rule. So this would be 0.3 times 0.9t plus 10, and then reduce that exponent by 1. 0.3 minus 1 is minus 0.7. So that chain rule is the derivative of the outside, 0.3 times this to the negative 0.7 times the derivative of the inside, which is 0.9. So that's the first derivative. So we have this times this times this times that. And I'm highlighting this because you can at this point use Excel and clean this up. What would you do though? You would multiply these constants, 10.2 times 0.3 times 0.9, and you get one number. You can put it in the front, and then you can take the second derivative of that. Well, I'm going to try to show you that you don't really have to do that. You may not like this, but I'm not going to go switching into Excel and simplify. I know this constant rule is my favorite rule, and when I take a derivative, if it's a constant being multiplied, I can just bring it down. So I'm going to bring down 10.72. I'm going to bring down 0.3. I'm going to bring down 0.9. Those are all my constants, and all I have left to do is take that derivative. So chain rule again. That's going to be negative 0.7 times 0.9 t plus 10. Reduce this by 1, so that's now negative 1.7 times the derivative of the inside, which is 0.9. So that's the second derivative. And when you're typing this in, you could say that that's 0.9 squared, or you can just type in 2.9s. But now I'm ready to put it in Excel. So I'm going to multiply the 0.2 times the negative 0.07, and I'm going to write this down. I'll come back, I'll have it written down, but it's c prime of t negative 0.014 t times e to the 0.07 t, and then the second one I have. Okay, so now I can take the second derivative of this, and so we need product rule here. So this is going to be the first times the derivative of the second. plus the second times the derivative of the first. Okay, let's catch our breath here. So this plus separates these two out, so I'm not even looking at this one. I'm just taking this derivative using the product rule, which is first, times the derivative of the second using the chain rule, e to the negative 0.07t times negative 0.07, plus the second times the derivative of the first. Now, plus this derivative, 0.2 is a constant, and then the derivative of e to the negative 0.07t is negative 0.07 times e to the negative 0.07t. So that's our second derivative. Okay, so now we have everything we need to answer all of these questions. I'm going to type these in off air. You type them in, we'll come back and see, make sure we have the same answers. Okay, hopefully you got them all typed in. Hopefully you remembered how to type an e function in. It's just exp parentheses and no caret there. And you can see I've got all my derivatives typed in. Okay, so now we can answer these questions. Remember, T is minutes, C is concentration in milligrams per liter. At what rate is the concentration of the drug changing 2 minutes after injection? That would be the first derivative. And so to interpret that, at 2 minutes, the concentration of the drug is, it's positive, so it's increasing at a rate of 0.45, and the units are, the Y units are milligram per liter, the X units are minutes. So at 2 minutes, the concentration of the drug is increasing at a rate of 0.15 milligrams per liter per minute. And then question B, find the acceleration or deceleration of the concentration of the drugs after 2 minutes, and that's the second derivative. And you don't just look at the negative of the second derivative, you look at the signs of the derivative and the second derivative, and if they are different, you've got deceleration, because this negative second derivative tells you it's concave down. The signs are different, it's deceleration. So we're going to say at 2 minutes, the concentration, because it sounds exactly like a IRC at first, concentration of the drug is, and the word would be decelerating, at a rate of 0.023, we'll say, milligrams per liter per minute. Then question C says, how many minutes after the drug is administered will its concentration be the highest? So this is what? It's asking for you to find the maximum. Okay, we want to know how many minutes after the drug is administered will you get your maximum, and then D is what is the maximum. So you have to really understand what we're looking for here. This isn't a second derivative question. This is a goal seek the first derivative to zero question. So here's our first derivative, and we're going to goal seek that to zero. And because we've taken our second derivative, we know that is a maximum, because this is saying, a negative is saying it's concave down, so we've got this shaped like this, concave down, and it's a horizontal line with a slope of 0, close to 0. This goal seek sometimes doesn't quite show you 0. So question C is, how many minutes after the drug administered? Well, that would be 14.12 minutes after the drug is administered. And what is the maximum concentration? That's what the original function is for. And the maximum concentration is 1.05 milligrams per liter. If you're not sure, if you're a little bit nervous, you can still go back to the eyeball method. Let's get some of these colors gone. And you can graph your function. Let's just get it a few minutes. Not sure if that's enough minutes. I could think it through, but I'm just going to throw a graph up here. There we go. If we counted by twos, we would see, or not. Okay, let's count by twos, and the graph will change on it for us. There we go. So we can see that we thought the maximum occurred around 14.12 minutes, and that sure looks like it to me. And you can see the concave down graph, and at 2 minutes, which is right here, it's increasing, but at a decreasing rate. See the concave down? So this is actually deceleration right here. Okay, and I just wanted to read through the interpretations that I've got written here in the key. And it says after 14.12 minutes, the drug concentration will be at its highest, and the maximum concentration is 1.05 milligrams per liter. So you've got two more higher order derivative problems in the lab manual. So definitely do those, and then come back and practice this derivative. Do it, 24 hours later. Try to do it again until you get really, really good at taking these derivatives like this.